welcome to the webinar. Good afternoon, or indeed perhaps good morning, or even good evening, depending on where you're joining us from, because we do have a worldwide audience for these events. So as John said, this is about why density is important for flow measurement for liquids and gases. So I will be, in the course of the presentation, covering a little bit on the background. What is density? Why is it important? What are the available measurement techniques for measuring density? Then looking at some of the methods for calculating density, both for liquids and gases, and summarize that. And then, as John explained, we will take any questions that have come in then and try and answer as many of them as possible, or get back to you with answers afterwards. Okay, so in many processes, density is used either for process control or product quality assessment, so it's used directly there. Equally, in many process applications, flow measurement is vital. And depending on the technology used, that flow rate may be measured by mass or by volume. But there is often a requirement to interconvert between these quantities. The choice of metering technology may be determined by other factors than the end units that you have to report in. So that's where density comes in, because it is the link between mass and volume. And you need to know it as a function of temperature and pressure. So density therefore becomes a fundamental part of a flow measurement system, one that's often overlooked, I guess, because it's sort of taken for granted. But as we'll see, accurate density measurement and calculation are vital and sometimes not as easy as you might think. So let's start with the obvious. Let's get an equation in there, get it out of the way right at the start. What is density? It is mass per unit volume. So in the SI system, the International System of Units, the unit of density is therefore kilogram per cubic meter. There are other methods of defining density. You can think in terms of relative density or specific gravity, which is a fluid density divided by a density of a reference fluid. So specific gravity there is the density of the fluid we're interested in at defined temperature and pressure, divided by the density of a reference fluid at stated reference conditions. For liquids, it's usually water that's used, most commonly at 1 bar or 1.01325 bar and 4 degrees Celsius, although other temperatures are sometimes chosen. For gases, you would typically use air, again at a reference pressure, 1 bar, 1 atmosphere, typically 0 degrees Celsius. But it's important to point out that a relative density is, although mathematically it looks like a ratio, it's not. A density ratio is the density of a fluid at defined temperature and pressure to the density of the same fluid at defined reference conditions. There are other ones I've mentioned. So you've got proof, which is commonly used in the brewing industry for referring to alcoholic drinks. API gravity, widely used in the oil industry. And there are conversions between them, as you can see here, for API gravity, relating it to specific gravity and therefore back to density. Okay, so that's what density is. How do we go about actually measuring it? Well, we can split density measurement techniques into two categories: offline methods and online or inline methods. And then in parallel with that, we need to think about how we actually calibrate those online or inline devices. Offline devices need calibration too, but that's generally easier. So, how do we measure density? Well, at a primary standard level, if we take a step back and think of flow, we can measure flow rate using a bucket and a stopwatch, plus scales and a ruler. If we want to do it by mass, gravimetrically, then we weigh the bucket before and after we fill it. And if we time how long it's taken us to fill it, we have a mass, we have a time, so we have a mass flow rate. We can do it volumetrically if we know the volume of the bucket, so we can measure the change in the volume of liquid in the bucket and again measure the time. Density, same principle. You can use a bucket, scales and a ruler for a gravimetric method, and that's the most fundamental method because that's the one that's closest to the SI definition of density, mass per unit volume. So we need to know the mass of the fluid and the volume that we have filled with that fluid. And there are a number of ways that that can be implemented in practice. So I'm going to go through the techniques listed here and say a little bit about each of them in terms of the technique and its advantages and limitations. So let's start off with hydrostatic techniques, which are fairly close to, again, the fundamental SI definition. And these are based on determining the apparent weight of a body of known mass and density when it's totally submerged in the test fluid, the fluid whose density you want to measure. Archimedes' principle. A number of ways of doing that. You can use a mechanical suspension system. So the body immersed in the fluid is connected to a balance by a fine wire. You can use, instead of a wire, you can use a magnetically coupled system. Or you can use a magnetic float system where the body is held in equilibrium by an electromagnetic field. And each method has its advantages and disadvantages. So here's an example of a magnetically coupled hydrostatic system. Basic equation, as I mentioned, we measure the apparent mass of the body when it's immersed in the fluid. That's m star. Separately, we determine the true vacuum mass of the body, ms, and its volume. And then from this simple equation, we can calculate the density of the fluid that the body is immersed in. Like all of these things, it's simple at that level. The complexity comes in trying to do that, for example, at elevated temperature and pressure. That's one of the reasons for using a magnetic coupling system, because you can have the pressure vessel inside a thermostat magnetically coupled to the balance system, which is easier than trying to have a wire coming out through a seal, etc. But then you're into well, you also need to know the effect of temperature and pressure on the volume of that body, because it will change with those. So there's all these second order effects that need to be looked at. Hydrostatic techniques have a number of advantages. They can be automated depending on the particular implementation. I've already alluded to the fact they can be used over a wide temperature and pressure range, particularly if you use magnetic coupling or magnetic float techniques, for example. And they can be very, very accurate, 0.005 or possibly even better, in fact, routinely 0.02%, because they're essentially a primary standard method. As I mentioned, it's almost as close as you can get to the basic definition. And they can be used for liquids and gases. Designs have to be different. There are different considerations because gas densities are lower, but the principle can be used for both. However, I've already alluded to the fact that if you're using them over extended temperature and pressure ranges, then you need careful design and you need to account for effects of temperature and pressure on volumes of components, secondary buoyancy effects, etc. If they're not automated, they can be very time consuming. You can be talking of a day to get one data point if they're not automated. Conversely, automating them tends to make them expensive because the systems that you need to do that tend to be bespoke and require, really one-off designs almost. And they're not really suitable for online or inline use because they are, as I say, more of a primary standard type of device. Next technique I want to look at are pyknometers, where you measure the mass of a known volume of fluid. So again, this is very close to the fundamental definition of density. You've got mass and volume. And again, there are a number of ways that you can do that. You can use capillary stoppered pyknometers, where you compare masses of equal volumes of a fluid and a reference fluid, typically water. Similar to that is the graduated bicapillary pyknometers, which again are calibrated with water. If you're working at elevated pressures, then you use pressure pyknometry techniques, again calibrated with water. Common theme here, water. Why do we use it as a calibrating fluid? Well, we know the density of water very accurately across a wide range of temperature and pressure conditions. So from that point of view, it's an ideal calibration or reference fluid, but there are limitations in other respects. One, it has a relatively limited liquid range, obviously, from 0 to 100 Celsius at ambient pressure. But the advantages in terms of density being very accurately known across that range make it the go-to fluid for calibration in those temperature and pressure ranges. What do these look like? On the left, we've got a capillary stoppered pyknometer. So basically, the idea there is that once you have calibrated the pyknometer with water, you then fill it with the fluid of the density of which you want to measure, and you insert the stopper. The small capillary there enables excess liquid to flow out, but what that also does is ensures that the pyknometer is always filled to exactly the same amount, i.e. to the top of the capillary at the top of the stopper, and you then weigh it. The graduated bicapillary pyknometer has a set of scales etched on it, and these are calibrated again using water. Pressure pyknometry is done using vessels like the one on the right, where you evacuate the vessel, connect it to the sample line, and then carefully open the inlet valve and just crack the outlet valve to draw fluid out through. Again, it sounds in principle a simple technique, but in practice, to get the best results, you really need to know what you're doing. And there are organizations, companies around who have that expertise. In terms of the advantages for pyknometers, as I've said, they're fairly fundamental. They're close to being, the SI definition of density. In general, they're simple, relatively cheap to purchase. Once you get into the pressure capabilities, it becomes more expensive. Anything to do with pressure puts prices up. And you can have good to high accuracy, and they can be used for gases and liquids. The glass pyknometers obviously are only liquid, but the pressure pyknometers can be used for gases. Again, careful design is required if you want to achieve those sort of low uncertainties. Careful operation as well, skilled operation. Again, it tends to be time consuming if they're not automated because it's manual, labor intensive. And like the hydrostatic techniques, automating it is possible, but generally isn't cheap. And they're not suitable for online. The closest is really the pressure pyknometer, which is a sampling, but still an offline technique. So if we want to do something in terms of online, where do we go? Well, oscillatory techniques are the preferred way to go. And that's where we measure the oscillating period of a body. And that can either be a vibrating tube filled with the fluid, or a vibrating rod or tuning fork immersed in the fluid, because there's a fundamental relationship between the frequency of oscillation and the mass either of the rod or of the tube filled with the liquid and density. So insertion densitometers, these are inserted directly into the fluid or perhaps in a bypass. So typically these would be tuning fork or thin-walled cylinder designs, and these can be used for online measurement for gases and liquids. Laboratory densitometers, offline instruments, typically use a small bore U-tube filled with the fluid whose density you're measuring. But the principle is the same. You're measuring a period of oscillation, and from calibration of the instrument, you can get a density from that. Other devices provide density output, flow-through vibrating tube densitometers, either single tube or multiple tube designs, typically used in the oil industry, for example. Coriolis meters, of course, in addition to measuring mass flow rate, have a secondary output, which is density. When they're providing a density output, they're doing that using transverse oscillation rather than the Coriolis twist for the mass flow. But again, a period output from which you can derive a density. Oscillatory techniques are simple and they're easily automated, and in general can be used over wide temperature and pressure ranges. The laboratory instruments with a glass tube are limited in the pressure range, but a Coriolis meter or a high pressure density meter can be used at extended pressures up to hundreds of bar, in fact. They're ideal for use inline, wide range available commercially, and potentially very accurate, 0.02 to 0.1%. And again, they are usable for both gases and liquids. They can be expensive to purchase, but that may well be worth it because of the benefits in terms of online, inline access to data, either for quality control or for safety critical applications. But one of the key points is that to achieve those very low uncertainties, careful calibration is required. And that's something that we'll touch on further on in the presentation. A couple of techniques just briefly. Compression and sonic techniques. Compression techniques are where you measure the change in length of a fluid, and you can do that using capillary rise, measuring the change in the height of a liquid in a capillary tube, for example, or the displacement of a piston in a pressure vessel, or by measuring the change in length of a sealed metal bellows filled with the fluid. And these techniques they're only suitable for liquids. Sonic techniques are where you measure the speed of sound in the fluid, and that can be done either using an interferometer with a variable path length or by optical diffraction, because there are thermodynamic relationships between the speed of sound in a fluid and its density. And that these sonic techniques can be used for both gases and liquids. So, we've seen there are a range of techniques available which can be used for gases and liquids. Some are only applicable to one, some are applicable to both gases and liquids. And the oscillatory techniques are generally the most useful for general lab and process applications and are applicable for gases and liquids. In general, if you want to achieve high accuracy, low uncertainty, then it will cost you more. But as with many things to do with uncertainty, low accuracy, low uncertainty doesn't necessarily imply low cost. It might just not be a good technique. I mentioned there the issue of calibration of devices, in particular the online or inline devices. For anything, recalibration at appropriate intervals is vital for maintaining traceability. In many sectors, particularly in the oil and gas sector, but in others too, calibration requirements are often driven by regulations, either implicitly in terms of the required uncertainty of a complete process for which density forms a part, or sometimes explicitly in terms of definitions for the uncertainty in density directly. And the key thing for calibration, and this is true for any calibration, is that it must be fit for purpose. What do I mean by fit for purpose? Well, in the UK, the regulatory position for liquid measurement systems for hydrocarbon production, and it specifies an uncertainty in terms of a dry mass. So 0.25% by dry mass for export into common transportation systems, shared pipelines in the oil sector. So that drives the requirements. Now, in the North Sea, it is changing, but until relatively recently, a significant number of the liquid measurement systems used volumetric flow meters, typically turbine flow meters. Allocation is by mass in the shared transportation systems, and the reporting, as we saw on the previous slide, is by mass. So the fluid density, therefore, is required to convert from volume to mass. And the most common way of doing that is an online vibrating tube densitometer. Traceable calibration of it is therefore required because it's forming part of that complete measurement chain. A long time ago, the approach was that these devices were initially calibrated at 20 Celsius on 1 bar, and then corrections were derived for other temperatures from measurements at 1 bar at other temperatures, and then separately at other pressures at 20 Celsius. But very frequently when these were being recalibrated, they were only recalibrated at 20 Celsius and 1 bar. But of course, these devices are used at non-ambient conditions, and the working equation that is used for them is cross-coupled in the output, which is the period, and the influence of the fluid temperature and pressure and ambient temperature on the densitometer. So, as a result of a joint industry project which NEL led, looking at the effects of temperature and pressure on liquid densitometers, the UK Oil and Gas Authority modified its guidance to require that densitometers for these fiscal applications should be calibrated at their anticipated operating conditions, i.e. simultaneously at temperature and pressure. Fine, how do you calibrate a densitometer? Well, easy. Again, in principle, use fluids of accurately known density. The fluids obviously have to cover the full operational density range of the device. They also need to cover the full range of other relevant properties, viscosity, speed of sound, etc. Oscillatory instruments are designed to be sensitive to a prime parameter, in this case density, but there will be second order influences like viscosity, viscous damping on the tube, etc. The fluid properties obviously need to be known across the full temperature and pressure range of the device because the fluids are acting as your transfer standard. So at the start of that project, we asked the GIP members, well, what range of conditions do we have to cover for this application? And you can see the outer range there went down to about 550 kilogram per cubic meter, so down into the condensate range, and up into the heavy oil range, up to almost 1200 kilograms per cubic meter. But the most common range at that time for the North Sea certainly was in the sort of 700 to 850 kilogram per cubic meter and up to about 10 centipoise. So we looked for and identified a number of reference fluids. That's fine. But as I mentioned previously, we need to know the densities of those fluids as functions of temperature and pressure. And for that, we used the NEL primary standard densitometer, which we've already seen before. Actually, it's this single sinker magnetic suspension densitometer based on Archimedes' principle. Low uncertainty, less than 0.015%, expanded uncertainty across a temperature range from about -40 to +150 Celsius and up to 300 bar. That's what it looks like, a complete system. So the quartz sinker immersed in the fluid whose density we're measuring, its apparent mass is transmitted through the wall of the pressure vessel by a magnetic coupling system out to the microbalance. How good's the performance? Well, over the course of the project, we made repeat measurements. Here's an example of measurements made at 3 different time intervals with 3 different samples of one of the reference fluids, toluene in fact. I've just plotted the results at 20 Celsius and 100 Celsius, and you can see that the agreement is within plus or minus 0.006% roughly across the whole pressure range between the 3 different samples at 3 different times. That's okay, but that's only internal. We have to look externally to make sure that we don't have any odd effects. So I've looked here and compared with similar measurements done on a similar system by PTB, the German equivalent of the NPL, NEL in terms of primary standards. And you can see the agreement with the PTB data is generally within 0.005%. Looking at the agreement with NIST, the US standards body, National Institute for Standards and Technology, there appears to be a significant shift. No density dependent slope, but a shift. So I dug a bit deeper behind that, and what I found was that the paper I'd taken the data from went into more detail about the samples that NIST had measured, and the equation that they had was an equation effectively covering 3 types of samples: their standard reference material, a degassed reference material, and an air-saturated sample. And you can see here that there is a split between the air-saturated, the standard, and the degassed. And our samples were actually closer to the degassed, and the errors then are down below 0.01%, down towards 0.008%, in fact, when we're comparing like with like. So that gave us a lot of confidence in the reference fluids. So once we've got the reference fluids, we fill the densitometer with 2 or more of these fluids in turn, control the temperature and pressure, measure it, and measure the densitometer output period. This is what it looks like in practice. On the left is the actual photo, on the right schematic. So you can see the densitometer mounted in an enclosure where we can control the air temperature round the densitometer. We circulate a reference fluid through the densitometer and control its temperature and pressure. And we measure the temperature and pressure. And you can just about see temperature sensor projecting in there and there directly into contact with the fluid. So separate temperature control of the air round the densitometer and of the fluid circulating through it. Obviously, we've got an uncertainty budget for our measurements of our temperatures, pressures, and our reference fluid densities. And we end up with an uncertainty of, well, depending on the reference fluid and the range of conditions, certainly better than 0.01%. Over the years since then, we have actually calibrated a number of these densitometers, 750 odd. Quite a few have come back. Some are regulars. We recognize them when they come back. Initially, we found that quite a few had errors, as found errors of between minus 0.1 and plus 0.1%. But using an average masks the scale of the problem, because in fact, if you split it, you see that positive errors are more significant. So over half had errors of over plus 0.1%, i.e. overreading. We didn't find any clear correlations with the as-found error between operating temperature and pressure, which had actually been a concern previously because the previous calibration procedure had only been done at, or recalibration procedure had only been done at 20 Celsius and 1 bar. There was a concern that as you moved away from that, you would see a bias. We didn't see that. But adjusting the previous, the coefficients, the K0 and K2 as per the previous calibrations would still leave a lot of the units with large residual errors. optimizing all of them over a plus or minus 5 degree, plus or minus 5 bar window always results in residual errors of less than 0.03. So, that's all well and good. You've got your nicely calibrated densitometer, and you then put it into service. But there are a number of other things which can affect the attainable uncertainty. And potential sources of error I've mentioned here are non-representative samples. So yes, these are online devices, but frequently not inline. Gas densitometers are often inline, as I mentioned, inserted directly into the fluid. Liquid systems typically run on a bypass. So depending on the configuration of the pipework, the operating conditions, flow conditions, you might have a non-representative sample passing through the densitometer. There's also obviously the possibility of inhomogeneity in the sample, i.e., as I've mentioned further down, the extreme example would be gas breakout in a liquid system, or possible density differences if you have components of extremely different density. Solid deposition on sensor elements is it's a fact of life, particularly for oil applications if you've got inverse solubility salts there. And that's why in general we tend to see over time densitometers, the error tends to go positive from one calibration to the next, probably due to small amounts of deposit on the tube, increasing the tube mass, which takes the error in the positive direction. Erosion of the tube material, for example, if you had a sand breakthrough event, would take mass off the tube, so the errors will go in the opposite direction. Gas breakout, as I've mentioned, worst case, it just stops outputting. And obviously stress effects. These are oscillatory devices, but they are designed to be decoupled as far as possible from external stresses, but you can never totally eliminate that. And of course, depending on the design of your metering system, if the temperature and pressure at the densitometer are very different from that at the flow meter, unless you correct, then you'll introduce errors. And that last point leads me quite nicely into the next part, where I'm going to look at calculation methods and why we need them. So for the first part, I'm going to focus on crude oil and petroleum products. These are typically sold by volume at reference conditions, which will either be 60 Fahrenheit, 0 psi gauge for imperial units, or 15 Celsius and 101.325 kilopascal. So the effects of temperature and pressure on the fluid density, the volume, are required to convert from measured to reference conditions. And this is done using volume correction factors, the most widely used of which are the ones developed by the American Petroleum Institute. These have a long history. In fact, the first recognized ones, the 1952 Blue Book tables, they then evolved into the 1980 tables, which were then updated as the Chapter 11 version in 2004 with I think it's a 2007 addendum. The 52 tables were called the Blue Book tables because they were a blue book. They were actually jointly published by the American Society for Testing of Materials and the UK Institute for Petroleum. Although they were published in 52, they were actually based on data really dating back to about 1916. And at that point, most of the samples that were used for developing the corrections were based on US domestic production in 1916. The 1980 tables had better base data and data handling than the 52 tables, a better database at that point representing somewhere about 65 to 70% of the estimated reserves in 1974. So still a bit of a time lag between the data and the publication. And they also implemented additional statistical checks. The 2004 correction, which again was a joint publication, moved entirely to algorithm-based calculations, so no printed tables. It extended the temperature and density ranges and also allowed combined temperature and pressure corrections. How do these things work? Well, for calculating these combined temperature and pressure corrections, the API Chapter 11 basically classifies petroleum fluids into three categories: crude oils, refined products, and lubricating oils. And they use a thermal expansion coefficient and compressibility coefficient, which is correlated in terms of the base density at 60 Fahrenheit and 0 psi gauge. There's one set of coefficients for the compressibility coefficients for all categories of fluids. However, there are several for the thermal expansion, depending on the liquid's classification. There's also an additional special applications category for the none of the above. So, as it says, if it's suspected of not adequately being represented, then basically measure it. Okay, how good are they? Well, the experimental data actually only went up to 49 bar gauge, 50 bar absolute. And the errors were assessed to be 0.1% up to that limit, but undefined above. But the correlations and equations extend to higher pressures. So you're into an area with undefined uncertainties. So for liquids, the API volume correction factors are widely used to convert from measured to reference conditions, and they are fit for their original purpose, which would be, as I say, converting from line conditions to reference conditions, or for converting between conditions at densitometer and flow meter. They probably wouldn't be good enough if you were using them as part of a primary reference system, and you would really need to look at alternative approaches there to get you to lower uncertainties. And that's in fact what we do on one of our facilities, where we have a volumetric reference system which is used primarily for calibrating mass flow meters. There are reasons for that choice. As I mentioned earlier, the choice of flow metering technology may be conditioned by other factors, such as the temperature and pressure ranges you need to operate at. But there we need to convert from volume to mass, and we use other techniques apart from API volume correction factors. Okay, that's liquids. Now, liquids in one sense are easy-ish, as I've explained, if they fall into these defined categories, the API categories. On the other hand, liquid state is actually the most difficult of the three fundamental states. Solids are pretty easy, they just sit there, and gases occupy the whole available space. So what about gases? Well, in some cases, gases are actually easier. For pure components or for certain well-defined mixtures, for example, pipeline quality natural gas, the easiest and undoubtedly the most accurate method for determining the density is measure the temperature and pressure. Don't try to measure the density, just measure the temperature and pressure and use an appropriate equation of state. So for pure components, for example, NEL has its own PPDS package, which covers a wide range of components. NIST, the National Institute of Standards and Technology in the US, have the RefProp package. And these are capable typically of calculating gas density with an expanded uncertainty of the order of 0.02 to 0.05% across a wide temperature and pressure range. For natural gas mixtures, the most commonly used equations are the AGA-8, the American Gas Association calculation method, and the GERG 2008, the European equivalent. Again, these have low uncertainties, 0.1 to 0.5%, depending on composition and temperature and pressure ranges. And these are widely implemented throughout industry. For mixtures, though, of course, you do need to know the composition. The AGA-8 and the GERG equations both allow mixtures with up to 21 defined components. The quantities of each of which have to be known. Typically, you could measure these online using gas chromatography, or take samples and analyze offline using offline chromatographs or other techniques. I've said, for pure components or defined mixtures, don't try to measure it, calculate it from composition. If the composition is not known or it's out with the equation of state limits, components that aren't in the equation of state, for example, then you really have no alternative but to measure the density using an online or an inline densitometer. So again, a lot of current interest obviously in carbon capture, utilization, and storage, and possibilities of either pure hydrogen or hydrogen blends into the gas grid. Again, for pure CO2 or pure hydrogen, just measure the temperature and pressure and use the best equation of state. For CO2, the Spann-Wagner equation, for example. However, carbon capture, utilization, and storage, we're unlikely to be dealing with pure CO2. There will be contaminants which will depend on the source of the CO2 and also on the capture process. So composition determination will be required if you're going to use an equation of state. In some cases, the contaminant levels will be low. So, to a first approximation, you could probably ignore them and you wouldn't be too far out for certain applications. On the other hand, if we look at the gas grid, for example, two schemes at the moment, at the one extreme, displace natural gas totally and move to 100% hydrogen. Your problems of composition, etc., go away. You just measure temperature and pressure, very accurate density calculation. Downside to that is it means changing burners in boilers, cookers, etc. Blending up to 20% by volume, you don't need to change burner technology, but you then have a mixture and you have to know the composition and use an equation of state. Now, AGA 8 and GER can handle that, but you still need to know what the composition is. And there is still the issue of how good are the calculations, because hydrogen in particular causes problems for equations of state. This is some work that my colleague, Dr. Idris Junaki, did recently, looking at the performance of 4 equations of state for mixtures with hydrogen. So this is for 10% mole hydrogen, 90% methane, not natural gas, but close to natural gas, across a range of pressures just at one temperature. And when you look at the graph on the left, you think everything's fine, all the equations are performing quite well. But when you look at the deviations on the right-hand graph between the calculated and measured values, you can see that, yes, the Gerg equation and the AGA 8 equation perform pretty well at these conditions for this composition. The Valderrama-Patel-Teja equation doesn't perform so well. Okay, that's fine. We'll use Gerg or AGA 8. Well, yes, but if we go to just about 20% hydrogen, 80% methane, we see that none of the equations are actually performing that well. And those errors would probably be unacceptable, taking that through the calculation process. You also need to think about the influence of gas density on measurement technology, some of which may be explicit in terms of orifice plate. So the orifice plate equation, there is the gas density entering explicitly into the equation for mass flow rate. But gas density also enters implicitly through the Reader-Harris-Gallagher discharge coefficient equation, through the Reynolds number, which is a function of density. It may influence other flow metering technologies. For example, in the case of ultrasonic flow meters, there is an implicit dependence on density, because an ultrasonic flow meter is returning a line integral along the ultrasonic path, the path velocity. but the path velocity is not equal to the true mean velocity of the fluid. In the case of a single beam, in laminar flow, you have a very pronounced profile, and you would get a large overreading effect in this case if you didn't account for the profile. Turbulent flow, it's less, but it's still there. Ultrasonic meters will typically use multiple paths, but they also carry out integrations based on the assumed profile, which is in itself a function of Reynolds number, again a function of density. So even where it's not obvious, density can influence the metering technology and may, once you're aware of it, influence your choice of metering technology. Similarly to liquid density measurement, there are potential sources of error. I've already alluded to some of these in terms of the calculation approach, measure temperature and pressure using equation of state. Again, if the samples that you have taken to obtain the composition are not representative, for example, if when you're taking your sample, you allow some of the lighter components to flash off, then the sample that you measure will not be representative of what's actually flowing through your pipe and through your flow meter. Using an inappropriate equation of state, as we saw there, for example, the Valderrama-Patel-Teja equation has limitations at certain conditions, but even what we think of as the best equations, the reduced Helmholtz type equations like AGA8 and GERG, have limitations, particularly either around phase boundaries in the case of CO2 or with hydrogen present. For direct measurements, similar considerations as for liquids. You can get solid deposition on the sensor elements and erosion, which will cause similar errors as for the liquid cases. Conversely, if you have liquid in there, you will get errors. And again, as with the liquid densitometers, stress effects and temperature and pressure differences can also possibly lead to errors. So that's been a whistle-stop tour of why density is important to flow measurement. And I'll summarize by going back to where we started and reiterating that accurate flow measurement is vital throughout process industry, from primary energy production from oil and gas that I've mentioned through to end products. Largely because, although we tend to think we live in a solid world, I'm sitting in front of a desk, there's a laptop in front of me, screen beyond that, solid materials. The majority of processing is done in the liquid state. The laptop has a plastic case that's produced in the liquid state. The desk that I'm sitting at has a fake wood finish on it, which will be a plastic produced in the liquid state. So flow measurement for process control is vital, and also for safety. And depending on the technology used, it may be measured by mass or volume, but very frequently you at some point in the process need to convert from one to the other. To do that requires a knowledge of the density of the fluid as a function of temperature and pressure. So the density therefore becomes part of the flow measurement system. And as we've just seen, it impacts both explicitly and implicitly with flow metering technologies. Fortunately, there are many techniques available for density measurement, but as with any measurement process, appropriate calibration is vital. And again, there are calculation methods available for expressing density at alternate conditions, either from process to standard or from one set of process to another. And density, as I've mentioned, is also used for process control and product quality assessment in many applications. And finally, just to put it into context within the UK National Flow Measurement Standards, in his introduction, John mentioned that these webinars are sponsored by BASE, and we also are part of the National Measurement System, which is funded by BASE. That provides the UK National Measurement System overall. NEL hold the flow measurement standards, and we have a number of facilities. Ultimately, for each of them, density determination, either by measurement and calculation at other conditions or by other measurement and calculation, feeds into all of our primary standard facilities and some of our secondary. So, for example, in the oil flow facilities, we have a gravimetric measuring capability and a volumetric measuring capability, primary reference. We calibrate both mass flow and volume flow meters, and depending on which reference system we're calibrating against, we need to interconvert between. EPAT, our elevated pressure and temperature facility, I mentioned, uses a volumetric reference system, but typically calibrates mass flow meters, Coriolis meters, so density vital there. Similarly for the other facilities, for the advanced multiphase facility, in addition to the interconversions, densities of the gas and 2 liquid phases are also used as part of the cross-contamination calculations. And one of our most recent facilities, our domestic gas metering rig, we need gas densities for pure components and mixtures as functions of temperature and pressure. So density is basically at the heart of everything that we do in terms of flow metrology, and it should be at the heart of your thinking when you're considering flow measurement systems. So that was the presentation, and I will now hand back to John for the Q&A.
Thanks for that, Norman. That was fascinating. So I think if any of you were wondering how significant density was to flow measurement, I think now you know. Okay, as you can imagine, we've had a load of questions, so we're fast running out of time, so we'll try and go through a few of those just now. Okay, the first one I've got for you, Norman. How good is the density output of a Coriolis meter?
That's a good question, John. In principle, very good if they're properly calibrated. And over the years, we have calibrated quite a few, and I mentioned, I think I said a figure of about certainly 0.1% down to possibly 0.02%. To get to 0.02%, you do have to do a fair bit of careful calibration, but yes, in principle, they're that good.
Okay, all right, okay. Is sampling an offline measurement good enough to calibrate an online or inline densitometer?
Not to calibrate. You could use it as a verification technique, because if you're trying to get a calibration, let's say, to better than 0.1% of your inline instrument, say you're looking to get to 0.05%, then your sampling and offline measurement has to be of a similar or better level. Now, there are some companies and organizations which might be able to do that. I know one or two personally who can. But that's not generally the rule. You can use it as a verification to say that your inline device is still broadly working okay. It hasn't catastrophically failed, but I wouldn't use it as a primary method.
Okay, all right. Right, I think we'll get time for one more quick one, Norman. Why does hydrogen cause problems when using equations of state to calculate thermophysical properties of fluid mixtures?
I kind of, yes, didn't cover that. I just said hydrogen can cause a problem. It's largely, it's mathematical and it's physical. Part of the reason is that equations of state are typically written in terms of reduced variables, reduced temperature, reduced pressure, reduced density. And the reducing parameters are normally the critical properties. So critical temperature, critical pressure, critical density. For a natural gas mixture, the critical properties for each of the components are broadly similar. So you end up with reduced parameters that are numerically roughly similar. Hydrogen, the critical properties are so much different that the reduced parameters have very different mathematical values, numerical values, So that's the underlying chemical physics of it. What that does is it causes the mathematical solvers that you use to struggle, and systems with hydrogen, even using the best equations like the Gerg equation, for example, sometimes for certain compositions just won't solve. Mathematical limitation.
Okay. Thanks for that, Norman. Right, listen, I know there's a whole load of questions here that we haven't had time to answer, but as I mentioned at the start, we will follow up with every question and answer them for you. As I mentioned earlier, also you'll receive a link to the recording for today's presentation. Please get in touch with us and let us know if there's any webinar subjects that you'd like us to cover for future. It's great to hear exactly what the industry needs and what the industry is interested in, so please let us know. Feel free to get in touch with me or send any queries to info.uk@tuvsud.com or visit the website www.tuvsud.com/UK for more information. Just one final thing, obviously the Global Flow Measurement Workshop is coming up in October. A lot of you will know it better as the North Sea Flow Measurement Workshop. A bit of rebranding been going on this year. We're open to bookings for that event, so check out the website, get more details on that. And on behalf of myself and Norman, thanks for your time today and enjoy the rest of your day.